All right, well, good morning, everyone. If anyone else is coming, they seem to be coming from a direction I don't anticipate, so we'll just go ahead. Nice to see such great turnout for our CQIQC seminar. And today I'm really pleased to be able to introduce to you, some of you have already met him, Professor Andrew Jordan, the Kennedy Professor of the Kennedy Chair in Physics, also the Director of the Institute for Quantum Studies at Chapman University. Andrew comes to us with a wealth of experience. He did his PhD at UCSB with Mark Skornitsky. He did a postdoc with Marcus Budeker in Geneva, and professor at Rochester. So some of you know him from that fact, where he was for many years. And about 5 years ago, he moved to become the director of this institute at Chapman University in California. Also, co-authored a thematic book on quantum measurement that some of you may have looked at, and it worked in areas too numerous for me to mention. But today he'll be telling us about one of them. He'll be telling us about his latest work on captured beam elements, which he's doing in Kindle.
Okay, good morning, everyone. Thank you, Ephraim, for this beautiful introduction. Thank you for coming to my talk. So I wanted to talk to you today about a topic, as Ephraim says, I work on many things, but I suggested a few different topics. And of course, Ephraim, knowing him, he gravitated instinctively and naturally to hone in on the quantum tunneling part of my work. And so I said, okay, well, I'll tell you about this new work that actually I'm very excited about quantum tunneling. This addresses, I think, a very fundamental question. And as I usually like to do, I hit sort of a little bit of a twist on the fundamental question, turns the fundamental into the technological as well. Another way of saying that, which is sort of a pun on my talk, is I'm making the virtual actual. So let me talk a little bit about, if we've not met before, just a few words about my background. So I'm, as Ephraim said, for many years, I was just across the lake in Rochester, and then I moved a few years ago to Chapman University. Here is Los Angeles, here is San Diego, where the weather is much warmer now than it is here. Chapman is in this little dot here, just north of Irvine, in the city of Orange, confusingly also in the county of Orange. And I live down here where all the hearts are in Laguna Beach. And here's a little picture of the university. So I have a little institute there. It's really very happy there. Good. So some of the things I work on, just in a couple of slides. So one of my ongoing interests is in the area of quantum measurement and control. And indeed, the subject of today's talk will be combining measurement with this process of tunneling. So various things I've worked on over the years. Also the application of quantum physics, but also surprisingly new things in classical metrology and precision measurements that I've worked on over the years, but also with various experimental collaborators in optics, but also in condensed matter physics. I worked also in the area of quantum thermodynamics, so topics about mesoscopic thermoelectricity, which will also enter into today's subject. Going back to my days working with Marcus Budeker in Switzerland, how to design miniature heat engines and refrigerators, topics of that nature. And then what my institute is all about, which is the foundations of quantum mechanics. So various topics about that. What is the wave function really all about? What's the deeper meaning of quantum physics, information, and all kinds of applications and esoteric topics in this foundational topics in quantum mechanics. And indeed, I would classify today's subject as sitting squarely sort of between these two areas. Okay, good. So the subject of today is quantum tunneling, and I assume most of you have encountered this in some way, but the simplest idea of it is if I have a hill and I roll a ball up the hill, unless I give it enough initial velocity, the particle will roll up the hill and roll back down, and will never get over to the other side. So in order to get over the hill, I have to give it enough kinetic energy to accomplish this converting the kinetic to the potential, and then going back here again. But schematically, in this little cartoon, the quantum physics doesn't need to do that. It can be able to have energy below this height of the hill and still be able to come out the other side. Okay, so this is a particle picture of this tunneling. And the way we usually learn about it in quantum physics is through the wave picture. We solve the Schrodinger equation in a scattering picture. So we have some kind of incident plane wave with an energy that's smaller than this potential barrier height. it becomes an exponentially decaying wave. For a matter wave, or for an optical wave, it becomes an evanescent wave, and it decays exponentially. But some little portion of it can emerge on the other side and continue on, so we can detect this particle over here, even though it has insufficient energy to overcome. So many of us have learned this from our early days studying quantum mechanics, and the fact that there are still surprises about this, or still things to be explored, I think is really a fun and exciting thing. So many people have been working on this. So here are a couple of papers. People have done experimental studies in tunneling time. I mention a couple of them. Importantly, because I'm here in Toronto, I have to mention Ephraim Steinberg's paper from 2020, measurement of the time spent by a tunneling atom within the barrier region. So this is an old topic people have been arguing about in quantum mechanics, because if I go back a slide, you can ask yourself the question, all right, if I as a particle enter into this tunneling barrier where I'm not allowed to be classically, and I exit at some point, it's a natural question to ask. If I have this idea, then in order to pass from A to C and B is in between it, I have to pass through B as an intermediate stage. And so then a natural question you can ask is, how long do I stay in this intermediate region B? And this becomes a very vexing problem immediately in quantum mechanics, because there's no time operator in quantum mechanics. And there's a long story I can tell you about this history of a time operator. It turns out there is such a thing as a dwell time operator. You can write down how long a particle spins in a region, and people have used those methods to explain and understand this question. But one of the interesting things is that different physicists approach this problem from different angles, and the surprising thing is they came up with different answers. One person says this, another person says that, another person says that. And so that's really why it's really beautiful to have these experimental investigations to be able to say, what does nature actually do? What kind of new surprises can we discover that goes beyond different theoretical approaches? But one of the ones I'll mention, just because I can, because I worked with Marcus Bodecker many years ago, the late Marcus Bodecker, he was a great man and a good friend of mine, is that he, together with Landauer, had this idea. And they said, well, how do you measure time? You measure time with a clock. So how can I make a clock to tell how long a particle spins in this region? They said, I know what we'll do. What we're going to do is that in addition to this forbidden barrier region, we'll equip the particle that's tunneling with a spin, and it has a magnetic moment, and we'll put a little magnetic field that exists in this area, and then we'll ask ourselves the question, when I detect the particle over here, suppose I prepare it, say, in the direction out of the plane, the spin, that is, and when I detect this guy over here, I can simply tell how much the spin rotates or precesses in the field, and that spin is like the dial of a clock. And so I can just read off the dial of the clock and say, aha, now I know how long the particle spent in the field. Ladies and gentlemen, come in. Please don't be shy. Come in, find a chair. Don't mind me. There are a few ones at the front as usual. They're last to fill up. Okay, and so I just mentioned that as one approach. It turns out that very simple-minded approach actually has surprises with it. It's not so easy, and people work to try to figure out. One of the facts that it's not so easy is it doesn't just precess like this, but it also goes up like that. And so it's like the dial of the hand of the clock pointing out of the clock face. So what do you do with that? Okay, so there's a story you can tell about that. I mention that just as a kind of background, is because these are some of the questions Ephraim has been struggling with over the years as well in his research. But what I want to stress today is we're not going to do that. I'm going to ask a new question. This is sort of the fun thing about science, is that we don't have to always rehash these old debates. I'm going to ask a new question about quantum tunneling. I'm going to ask what happens. Suppose I can actually, as the particle comes in, okay, now I can only be so cheeky because now I have more people than seats, but at least I see 2 seats right here. So you guys come on up forward and have a seat. Otherwise, you'll be very uncomfortable listening to me. I think there's one more chair back there. Very good. And you're right here. Okay. So the question I'm going to ask is the following. Suppose I can ask the particle, as it's doing this tunneling process, I can ask particle questions. I can say, particle, are you there? I can do a measurement of the particle, and I can see how this affects the tunneling. So that's the kind of question I'm going to be doing. And in particular, I'm doing a particular kind of measurement. I'm looking at a continuous measurement, and I'll tell you what that is. And I want to ask about the following questions. I want to ask, how does this tunnel barrier occupation change? And how does the tunneling rate change for different measurement strength? So I can imagine I do a very weak measurement where I very weakly probe the system gently and say, are you there or not? But then I can turn up that strength and measure very strongly and ask, for sure, particle, you have to give me an answer. Are you here or are you not here? All right, so that's the kind of question I'm interested in this talk. Okay, so I'm going to begin the talk with a little puzzle. And if you don't remember anything about this talk, just remember this little puzzle, because I think it's fun. So the idea is the following. We kind of have a little paradox here. So we know that the particle does not have sufficient energy to classically exist in the forbidden energy. It's classically forbidden. One way of saying it, it's in a virtual state, not in an actual state. But what if we measure to check if the particle is in the forbidden region? So according to the axioms of quantum mechanics, it has to either be there or not. If I do this measurement, the well-posed question must be answered if I do an experimental measurement. And there are sort of two things that can happen. There's a yes and a no. So if it is there, if I find the particle, yes, it's in the tunneling region, where did the energy come from? Because I didn't give it initially enough energy. So if it's there, it has to have enough energy to be there. So where did the energy come from? But if it's never there, then the tunneling never happens. And I never see it happen on the other side. So either we kill the effect or we create energy. So this is the puzzle. This is the tension I'm giving to you to motivate this talk. And we go from here. And if anytime you have questions in the talk, don't be shy. You can just ask me and we can chat. Okay, good. So when I started thinking about this problem, I started thinking about how we could do this measurement about the particle being in the square tunneling barrier. And I realized this is experimentally going to be really tricky. Probably Ephraim has some clever tricks to do that. But there's a simpler version that we thought would be more experimentally relevant and also maybe equally interesting, but also has all the conceptual richness of the original of the question, which is this little system I've drawn here, the series of circles, dashes, and lines, which I'm going to explain to you what these things are. So what I have in mind is a mesoscopic experiment involving a source and a drain that are macroscopic, or let's say at least mesoscopic ohmic reservoirs that can give particles and heat, electrons in this case. This is an electrical conductor diagram. And these three little circles here represent quantum dots that can have single occupation. So electron can either be there in this dot or it can't be there in this dot. And what do these lines mean? The lines refer to the energy the occupied electron would be allowed to have. Okay, so as I go into this dot, I can change the energy, for example, by applying the gate voltage, plunger voltage nearby, so I can tune the energies of these dots. And the idea is that the first dot has an energy epsilon, the second dot has an energy, if it's occupied, epsilon plus delta, and the third energy dot has, again, an energy epsilon. There are some rates of tunneling from the left dot onto this central dot. There are some rates of tunneling from the right dot onto this right reservoir. And then there are some couplings, omega, that couple these dots that allow hopping back and forth between the dots and so on. Okay, so let me, this I'm focusing on this upper diagram. So this is, again, the left ohmic reservoir, the right ohmic reservoir. And these are the things I just said in words down below written in text. Okay. So what's the physics here? The physics is I can, for example, apply some bias to the left reservoir compared to the right, making an electrical circuit through this loop. Electrons can come onto the left dot. If I could only have elastic transport, that would be the end of the story. Nothing can happen. But what can happen is that I can have a virtual transition where I can effectively tunnel or occupy the state virtually, and then come down here to the right dot, and then exit to the right reservoir. So there can be tunneling through this process using that state that's energetically forbidden nominally as a virtual state. And this, in mesoscopic physics, this is called a co-tunneling process. Okay, So the central dot for us acts like a discrete tunnel barrier. And because it's discrete, it simplifies some of the theoretical analysis and makes it conceptually more tight. Okay. So that's the first part of the story. That's the tunneling aspect. Okay, so people have studied this for many years now in mesoscopic transport. And now and so how do you do this? Right. So you can write down Hamiltonians for this. These are involving fermionic operators. So this is the Hamiltonian of this so-called triple quantum dot system. So you have occupations of the first term. These omegas give hopping, for example, from this dot to the right dot plus their emission conjugate, and so on and so forth. Okay. So that's the upper part of the circuit. Now, what about the lower part of the circuit? Okay, so the lower part of the circuit, that's going to be our measurement. That's going to be our way of interrogating this tunneling process. Because we know, because these are electrons, they also have a handle upon them. So before Ephraim was thinking about the tunneling time, we had the spin as the handle. Now we're going to use the charged electron as the handle to see, are you there or not? Okay, and the way we're going to do that is because if this dot is empty, it's going to have a capacitive coupling to some nearby conductor, and it's going to be different if it's occupied because there's a charge there. And so this nearby conductor is simply a charge sensor that's going to be our measurement device to say, is this guy going to be full or empty? And the way this works is, again, we have another electrical circuit. We apply a bias across this when we measure the current flowing through this so-called quantum point contact. Okay, in the physics of the quantum point contact is such that there's a transmission. So this is like a scattering process, mesoscopic physics. And the fact electrons can make it through here or get reflected is a stochastic process described by a transmission, which we can calculate from a scattering matrix. So the transmission is T0, we'll define it to be T0 when it's empty, or this upper guy is unoccupied. But when it's occupied, it pinches off this contact, it changes the resistance a little bit. So T1 becomes T1 when occupied. Okay, so the fact that there are different transmissions, according to Bodecker and Landauer, tell us that there are different currents passing through this conductor. And so with that equipped in hand, we can also then learn about the fact that this is a measurement because I can look at the current and figure out indirectly if this guy is empty or full.
So you never have current flow from the central dot into the probe, the Hamiltonian commutes with the occupation number in that middle dot.
That's right. So here you see there's a capacitor. So this cuts off any direct transmission from the dot from here to there. Right, so it's only capacitively coupled, not tunnel coupled. Okay, so since it's electromagnetic environment, good. But I mentioned before there's a possibility of transmission and reflectance, and because of these two possibilities exist, there's also noise in that current, and that noise is called shot noise. So in the photonic context, you're maybe familiar with this. It has to do with the fact that there's granularity of the photons on your detector. The same thing happens with fermions. So there's granularity of the detector on the fermions. And so there's noise. And so we can ask ourselves the question, and if I think about this as some noisy signal, how long does it take to distinguish signal from noise? We can calculate that, and that gives rise to a characteristic measurement strength. Okay, and when I can distinguish signal from noise, that essentially tells me how long it takes to do that. And so the strength of the measurement then involves the sensitivity. The difference between T1 and T2 goes in the numerator. The power of the shot noise goes in the denominator. There's also some voltage here and Planck's constant. And this is the thing I can tune, essentially, for example, by changing the transmission difference or by changing the voltage to be able to detect how strongly I measure this central dot. Before I go on, are there any questions of what I said? Is it clear? Yes? This measurement strength can be anything between 0 and infinity. Okay. So infinity means like I have like a perfect instantaneous projective measurement, and 0 means there's no measurement at all. Okay.
Sorry, Andrew, can I ask one more question online? So,
Sure.
What is V, the voltage?
V is the applied voltage across the quantum point contact.
Oh, okay.
I'm surprised there's no resistance. I would have thought it depended more on the current as we're talking about shot noise, and also no temperature.
Okay, good question. So the fact there's no temperature is because I made an assumption I didn't tell you about, which I assume that the EV is much bigger than KT in the system. So the shot noise dominates the thermal noise. That's why there's no temperature. And the fact that it involves the resistance, well, it does. I've written it in a funny way. It's because the conductance of a quantum device is given by E squared over H, the quantum of conductance, times the transmission, or the energy integrated transmission, because that's all kind of smuggled into here, and also the definition of the shot. So all those quantum resistances are hidden in, for example, as E over H. Good. So let's talk a little bit more about, okay, good, this quantum point contact. So measurement can probe the occupation of the central dot strongly or weakly, again, if this gamma parameter is 0 or large. So the strong probing means I check quickly if the particle is there compared to the tunneling on or off the dot. So there's a time scale consideration there. Whereas the weak programming, roughly speaking, we say the measurement gives us a noisy hint if the central dot is occupied or empty, because I have some hint, maybe it's, if the current goes up, maybe it's more likely to be empty, but that could just be a fluctuation of the current as well. Yes.
Sorry, one more question, comes back to Andy's. This gamma measurement string, is there not dimensionless? So there's units of frequency, we're going to compare.
It has units of time, that's right. It has units of time. And so so basically the relevant strength, so the actual amount of collapse, so to speak, is that rate times the time of measurement, right? So that's the whole thing about a continuous measurement. Is a continuous measurement that takes time. And I'll say a few more words about that in the following slides. Because this is something you don't learn about in your quantum mechanics textbooks. You just learn about projective measurement.
But before you said that gamma is infinity, is an instantaneous measurement, and gamma is 0 is no measurement.
That's right.
So it's 1 over time. It's not 5.
Yeah, it's a rate. It's a rate. Yeah. Good. All right. So when we start talking about continuous measurements, measuring the system in a continuous way, that there are two types of these continuous measurements. And one is what we call diffusive quantum measurement, and I'll say a few more words about that shortly. And the other is a so-called quantum jump measurement. So often in quantum optics, we're more familiar with this kind of quantum jump measurement because, for example, we excite an atom and we have a photodetector sitting in our laboratory and we wait and we wait and wait. And eventually we get a click. And when we get a click, the atom, we reassign it from whatever state it is down to the ground state because we know how the atom has emitted the photon, for example. That's so that we're more familiar maybe from quantum optics with this kind of measurement. But maybe also but this diffusive quantum measurement in quantum optics would be something like a homodyne or heterodyne measurement where you get a continuous noisy result. And that's more like what we have here with this quantum point contact. We have this noisy current that we're measuring. But we can also do quantum jumps, and I'll say a few words about how to do that in this context as well. So let's talk a little bit about quantum measurement and quantum trajectories. So one way of thinking about this continuous quantum jumps, I mentioned this diffusive and the jump ones. So the diffusive one comes into play when there's a quasi-continuous stream of data coming to the observer. I've illustrated that here with this measurement record. So this can be some device in my laboratory, say some oscilloscope after I've amplified the results of my measurement. So this is actually sitting in data in my laboratory and has some kind of stochastic process I've written in a discretized way here. And the idea behind the quantum trajectory theory is that we know when I get this bit of information, I have to change my mind, or I should change my mind about what the quantum state of my system is. And I do that in a continuous way. So then I reassign my quantum state based upon the record. And so what happens is that this diffusive Brownian type motion of my detector becomes a Brownian type motion of my quantum state of the quantum system living in its Hilbert space. Whereas jumps usually occur when there is a sudden information coming. This is more like a Poissonian process rather than a Gaussian process as a click, right? And so examples of that are given over here, for example, in this classic experiment, looking at some 3-level system and then measuring some fluorescent counts where you have on, off, off, on, off, on. These are the kind of quantum jump type processes. Yes.
How does this approach handle kind of the uncertainty in your knowledge in the continuous measurement of the?
Yeah. So that's the whole game, is it? Because when we get this random fluctuation, you kind of have two hypotheses. One, you can say, it's the system doing this. The record is responding to my system. That's one hypothesis. But the other hypothesis is, no, this is just noise from my detector. This is just some kind of random fluctuations. And the fact that both of these can happen simultaneously, you have to factor that in as both things happening. And so this approach can be thought of as a kind of Bayesian approach, where you have some probabilistic outcomes, but there is some signal in that as well. And so then you update your probabilities appropriately based on information I obtain. And so this is like a quantum version of that, where I update not the probabilities, but the state itself.
I guess my question is, maybe this is a cartoon, but you're plotting the wave function as a function of time.
Yes.
And having a wave function implies perfect knowledge of the system.
Yes.
Instead of pure state.
Yes. And maybe that's the radical thing about this, is that because indeed, so what happens is that as long as I have efficient detectors, but I don't lose information, it turns out that that's what you just said is absolutely true. If I plot the wave function and the function of time, I do have perfect knowledge. And so you can say, well, how do I know? How do you know if you have perfect knowledge? Well, what you can do is you can stop, say here, and say, according to my theory, this should be the state. I'd stop, and I can do conditional measurements and say, do the results of those, are those consistent with that state assignment? Right? And if they are, then I'm right. And if they're not, then I'm wrong.
And how does this get modified? Inevitable case we do have information on.
Good. Yeah. So when you do have information, if your detectors aren't perfect, of course, you replace this state with the density matrix. And so then what happens is that imperfection of knowledge tends to lead to an effective decoherence. Okay, but not perfect decoherence, but some effective decoherence that you have to take that into account as well.
So basically you have a quantum trajectory and density matrix space, and if you need your density matrix to start with, and the measurements, including some understanding of the imperfection, you can actually trace out.
That's right. You trace out conditionally upon your record what it is. You got it. Good.
So can I ask a question here? I mean, is your wave function include everything? Like, it's just the central dot, but how do you decouple from the rest of the system? So
Good.
you have problem?
Good. Yes. So what we do, and we will come back to this in a minute. What we do is we focus on one thing, right? So in this case, we're going to be focusing on these three dots and looking at the state of this triple quantum dot system. So that's the thing the state I'm going to be tracking. Okay. So
assuming a total occupation number of no fluctuation in total electron.
No, there can be fluctuations. So 0, is an allowed quantum state, for example. Okay. Yeah, but how the coherence of that with 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1, those are the four possible states of this.
You don't allow 1, 0, 1.
No. That would be yeah. I don't think we allow 1, 0. Only one electron the whole time in this system. Yeah. Yes. So we're tracking the state of, in this case, this system as a function of time.
But your V is a bias voltage to the left and right. Right? So your lead is connected to the gamma.
That's right. Yes.
So how do you integrate out that environment?
That's
where charge fluctuations.
That's right. So we do have equations that inject electrons into that, and so that's part of the front. So I'll show you equations here a little bit later. Maybe that will make it more clear.
But I'm curious though, the V, I thought that was the voltage only across the QPC.
That's correct.
It's not
That's
actually
correct.
across the-
This V here is only for the red box.
No, there's a battery there.
There's a barrier.
So it's
Yeah.
different
So yeah,
voltage.
But you
battery.
have to give us a bias voltage to start the process.
That's
Yeah,
right.
I just don't think it's the same V though.
So there, yeah. So there can be yes. So what are the relevant energy sources here?
Yes.
So one energy source is the voltage of this battery. Another energy source could be the voltage of this battery, for example. But I can also have different temperatures here of these left and right, and so that will also come into the source.
But that comes back to Forrest's question. If you're really treating the finite temperature, then even from the beginning, you don't have low functions.
Correct.
So-
Correct. Good. Yeah, and again, I think this will be clear in a little bit. We're going slowly.
Sorry.
Sorry.
That's
Good.
the game.
That's good. Good. Yeah, and so this just gives you a few cartoons that these devices actually exist in the laboratory. So these are pictures of samples people built. This is already more than 20 years ago, these samples. And so they can then, so the idea is that these two things act as my double quantum dot. What are these? So this is a two-dimensional electron gas. The little shading on top, these are metallic top gates people will put on them. And by applying voltages, they can confine the motion of electrons in these two-dimensional structures. So here there's one electron that can bounce back and forth between one of these two dots. And then by applying current against source and drain, I can drive current through this quantum point contact, again, having one of two possible currents. And the relevant time to distinguish signal to noise, that's the inverse of that thing I showed a minute ago. This is a more general formula. It's the ratio of the shot noise of the zero frequency shot noise divided by the difference of these two guys squared. So this is the typical time scale associated with the measurement. So it takes time in order to say, am I left or right? Good. So what's amazing is that these kind of quantum trajectories have actually now been seen in the laboratory. So the first experiments of this kind were done in superconducting quantum circuits. So the idea is that we can prepare, for example, the system. This is a two-level system represented as a block sphere. We can prepare it in sigma x eigenstate and then measure continuously in sigma z. Here, the method of interrogation is different. I'm using microwave frequency photons to dispersively measure the state of this qubit. Let me go back. But maybe one nice thing is I can draw a little cartoon here, a little movie. And this is actually data that shows how the quantum state is continuously updated as I measure continuously. And you see that there are fluctuations, but eventually the system settles down on sigma z is +1. So I'm measuring the spin up. But you see it doesn't immediately go there. It goes under this kind of random process that eventually settles down up there. So this is going to be the sigma x and sigma z quadrature. The line is the theory. The dots are the data points from experiments showing that this actually works really well. Then the kind of formulas you have to solve are schematically represented here. There's a deterministic part of your density matrix, and there's some stochastic part that you have to also input to be able to generate this kind of solution. So the nice thing about this is that this gives us a really deep foundational insight into quantum measurement process. So it's no longer a mysterious sort of black box, but we can actually interrogate in a scientifically rigorous way how this collapse happens in a continuous way in this kind of experiment. Yes?
So I was curious how this evolution, how this equation corresponds to occur, because the stochastics there, if you simulate them to get sample the trajectory, so is the theoretical calculated average over samples? And if yes, then
No. This is a single realization of one experiment. And so how you might say, how does the realization of the Wiener process correspond to the experiment? It's the same Wiener process that appears in my measurement record. So I talked about the measurement record before. So what you do is you take that record, and that basically acts as the feeding for this process. So that's where the sample comes from.
kind of the choice of the realization of this stochastic jumps from this to the data.
Yeah. So so what you do is basically you say schematically that the record is like the expectation of the observable you're measuring plus the stochastic term. Okay, so that's the way you theoretically model it. Of course, in the data, you just measure the left-hand side. You measure some number, right? And then from that, essentially, you can back out the right thing to put into this equation to integrate this equation. Good. So again, this is data this is a paper in 2013, Irfan Siddiqui. And the top panels, these are the ensemble averages of many runs of the data, where you see sigma x, sigma y, sigma z. So you see a decoherence kind of process where you lose coherence as a function of time in sigma x. Here, this is actually on the other panels are when you start driving at the same time. So I'm not just measuring anymore. I'm measuring while I drive. That's this omega going along like this. And so for you, now you see not only decay, but oscillations with decay and so on with stronger oscillations. But down in the lower panels, you see this is actually a single realization of the experiment. And you see, actually, if you look carefully, you see two curves. It turns out one of the curves is the theory, and the other curve is the experiment. And so you can say, well, how can I test for a single realization what happens? And essentially, the way you do it is that you do this a billion times, and you have a catalog of all possible state assignments for the state. And the way they validate that is they say, I'm going to integrate for some time, I'm going to measure it for some time, and then I'm going to stop. Say I stop here, and then I do my conventional tomography on those samples, and then I check what's the right state assignment to do like that. And they do that, billions of times. So this is a very precise validation of single trajectories of this form. Okay. So just showing you a little bit more about the how this works in experiment. Yes.
So you're basically post-selecting and having the same continuous measurement record in that single realization. So you're taking your billion samples, you're finding the 1,000 will have the same continuous record for the first 1 microsecond. And then you're doing quantum state tomography.
It's almost that, Boris, but not quite, because that would even require more resource intensive, because that means you have to have exactly the same or nearly exactly the same trajectory, which is very, very, very rare. And so what they do is they look at trajectories that give the same state assignment at that time. So it may have different trajectories, but at that time, they all agree on what the prediction is for the state at that time. So this is the way they do it.
This might be a stupid question, but what's the sigma X and Y and Z in the transmons?
Right. So in the transmon, it's basically, so it's a Josephson junction-based quantum circuit. So there's an anharmonistic, this is, I've done the so-called transmon qubits. So there's an anharmonistic quantum oscillator. So they use the lower two levels as their qubit. And so that provides their two-level system. So sigma X, sigma Y, sigma Z is sort of the usual polymatrix expression of those, of the two-level system.
So here is that why is that sigma X is the only one that the coherence?
Because we're only starting in the sigma X equal +1. Yeah, you see the initial state is sigma X is 1, sigma Y, and sigma Z is 0.
So base matters between the two levels.
They matter, absolutely.
But the continuous probe is just a sigma Z.
Sigma Z, exactly. Yeah. Good. So there's a little analogy I published back in 2013. So the idea is that if you think about these trajectories as like butterflies in a cage, you have a bunch of butterflies, they're like the number of experiments you run. And if you let the butterflies out of the cage, sort of in the old days, you'd say, okay, the butterflies eventually settle on the left tree or the right tree, and I can count number of butterflies in the trees and tell you about statistics. And this new kind of way of doing it gives a deeper insight. It tells you how the butterfly gets from the cage to the tree through some winding path. So it's a little analogy, just kind of for fun, I thought, to help you remember this idea. Good. So just a few slides about form. I'm not going to go much into the formalism. I don't want to bog you down too much, but these are the kinds of equations we write down. So this is for our equation. I think maybe to answer some of the questions you talked about before. So what are the basis states? Essentially, the basis state is the zero state where everything is empty. And then the single occupation, the left dot can be 1, the center dot can be 1, the right dot can be 1. And so we write down equations for this triple quantum dot system. So there's a Hamiltonian I wrote down a few slides ago, maybe you remember it, H triple dot quantum system. That's the Schrodinger form. And then you have to do the open quantum systems part. So you add in these Lindblad dissipative terms, and this accounts for two things, right? So the first thing is it accounts for the fact that we have transport on and off the leads. So that's done in an incoherent approximation with these operators like so. So that's the part where you enter and exit the system in this open quantum systems approach. So these are jumper operators into and out of the leads. But the other part of the story is that we have to add in the measurement part of the story. And so there's another part over here, gamma L gamma, and that accounts for the quantum measurement, the continuous quantum measurement. So there's a dissipative part. So this would be like the Lindbladian type form, this first part that you would have with these operators. So what's the operator you're going to be using? It's just, is the central dot occupied or not? It's CC projector with this rate of measurement. So I'm asking the question, dot, are you there in the central dot or are you empty, right? That's what this is. Effectively, this equation is answering that question. And then there's that random part as well, the stochastic part, and that's the second part as well, the stochastic Wiener process, and that accounts for the randomness that happens in the shock noise of the quantum point contact. So that's the kind of the formalism that we need to solve for this problem. But without getting in too much into the math, yeah, so we can just say in this kind of, just to give a simple example here, in the weakly responding regime, where this is a continuous weak measurement, if I ask just for a simple thing, what is the CC occupation, rho CC, not the whole thing, but just this guy, I can write down an equation just for this part of the coupled system. I see it involves a part where I have hopping or coherent transitions from the left and the right dots. And there's a part that involves the randomness from the quantum point contact that involves the measurement strength and the occupation of the central dot. So when I solve these equations, what do I get? So this is the kind of solution that emerges for this rho CC. This is the occupation of the central dot as a function of time. And what you see, these are several different, so I have three colors here. I have blue, I have yellow, I have green. Those are three different realizations of that stochastic process. And you see what something is very interesting happens. Remember, this is in the tunneling regime. This is strongly detuned. And you see that, for example, green, it's basically empty the whole time with some fluctuations, as you might expect if it's like a tunneling process. And yellow, something weird happens. Sometimes it has the fluctuations up to like 0.1, then it comes back down, a little bit of fluctuations, almost zero the whole time. But something weird happens for green. It's like 0, 0, 0. And there's a jump. It jumps up to like really 1, around 1, and it comes back down. And so what we find by realizing this is that most of the time, effectively, it's either empty or it's full, which is something I didn't expect. I think it's really interesting with these transitions kind of.
So this is when the measurement is strong with respect to the other rate?
This is weak. This is a weak measurement.
That's surprising.
Yeah. And so you see this kind of thing. So this is a stochastic evolution.
Explain why you're saying
You see that because most of the curves are down here near 0 or up here near 1. And there's a few jumps in between, but the jumps are a relatively small fraction of everything else. Like most of the time, I'm kind of around here or I'm around up here. That's all I mean by that. Yeah. Right. So here it's near 0. Here it's near 1. There's some little bit of jumps, but the spikes are infrequent.
Well, what about yellow and green sets? So
Yeah, so green is also around 0 mostly. For me, for my eye, there's a few little fluctuations, right? Again, there's noise, but mostly empty. If you force me to describe that in a word, that's what I would say. Okay, but now, yeah, so these are three different realizations of the process. So the idea is I turn my detector on, I record my current, I solve my equations, and I plot the occupation that I infer as a function of time. I do that 3 times. Here's our 3 representative solutions to those equations.
C is the central dot.
C is the central dot. It's the occupation of it. Is it saying, is this dot empty or full? That's what this is telling me. Okay, so now you can ask, well, give me a more sweeping thing. What if I average over everything? What's the average occupation of this dot? And here's a really cool prediction. This is our first prediction that we're making. That's kind of, I think we can check this in experiment. I'm plotting the average occupation of the dot versus on this axis, delta. This is the detuning, how big the tunneling has to be on this axis. And this is the measurement strength on this axis. Okay, so this is for the occupation. And this is for the tunneling current. This is the current I predict through the triple quantum dot system. You can measure as an average. The first thing to point out is suppose I turn the measurement off. There's no measurement. As a function here, you see this goes down like 1 over delta. And you can do this calculation quite easily. There's an effective tunneling rate that goes like the coupling rate squared divided by the detuning. So this is the co-tunneling process. The bigger the detuning is, the more unlikely this transition is, and the more empty the dot becomes. Okay, so empty, empty. So down here, when omega, again, delta over omega is 10, it's really tiny, like 1 over 100. But basically always empty. Right? As you would expect, it's more and more energetically forbidden. But now, suppose you start turning the measurement on from 0. This is the measurement strength on this axis, and something interesting happens. It begins to grow. So the occupation begins to grow more and more and more and more and more. So it's the electron is occupying the dot more and more and more and more. And eventually it plateaus for a value of around 1/3. So around 1/3 of the time now, the electron is actually occupying that dot for strong measurements. So that's the prediction about the occupation. For the current, it's a similar story. Again, the current goes down like 1 over delta, reflecting this co-tunneling process, so I have no measurement. But when I turn the measurement on, something very interesting happens. First, the current starts to go up. the tunneling is actually helped by the measurement. It goes up, 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 and then but then eventually it starts to go back down, 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 down. So what's going on there? Well, this is our prediction. We say that this should be like this is a measurement assisted tunneling effect, that as I turn the detector on, the tunneling increases, so the current goes up, but then it goes down. So what's going on there? How can we kind of make sense of this? And one way of understanding it is simply the fact that as I start measuring it, I'm sort of shaking the system up. I'm allowing more occupation of this dot. It allows me to again convert the virtual to the actual electron is actually on the dot, and then it can find its way out to the other side. But then if I start measuring really, really hard, and I ask myself, are you there, electron, on this dot? It tells me, yes, I'm Andrew. I'm here, I'm here, I'm here. And if I keep asking it again and again, it has to give me the same answer. This is the quantum Zeno effect. So, yes, I'm here, I'm here, I'm here, I'm here. I tend to pin the electron either on the dot or off the dot. And that again inhibits the tunneling because it can't find its way off the dot. So this is like in my view, this is like a Zeno-dominated regime, and this is this measurement-assisted tunneling effect. Okay. Questions? Is that clear? That's the prediction.
Does this prediction depends on your gamma L, right? So you're given a number, so is there a jump in the 1/3 or half or something? Or?
Yeah, so this depends a little bit on the other parameters of the system, and it also depends on how, so it also depends on the fact that I'm measuring just the central dot. So it turns out if I measure the central dot, say, and a little bit the left and the right dot as well, that also changes the story a little bit. I can talk more about that, but this is maybe the conceptually simplest case.
I'm just wondering if there's a plateau here. Like 1/3 is like a, kind of plateau, and then you jump into the half depending on these values that you are changing.
Yeah, we've explored that. So I think you can find cases where you can get up to a half if you play with the other parameters of the system.
Not if you keep the two epsilons.
Not if you keep the two epsilons the same. Yeah. I don't think so.
Can this all be understood just by thinking of how you're perturbing the energy of the central dot? That you're broadening the central dot, that makes the virtual state more accessible.
The Swift student, very good. That's good. So yeah, so Ephraim says, okay, think about it another way. Think about maybe because you're averaging over everything. Maybe you're just kicking the system. You're applying some fluctuations. So if you think about disturbing the system, you can also think about it another way, which rather than having a sharp line at this point, maybe you're like broadening the line. And that's another way of thinking about it. I think that's an equivalent picture. So that's a good point. There's another question.
Yeah, I think we would imagine instead of doing measurements on the average value of versus to see, doing something like measurements on its standard deviation and things like that. It would have helped you predict this like mostly operation of either 0 or 1 in there.
Yeah. So with this formalism, you can predict now, for example, you can also predict like the variance of n as well. That's also something you can predict and calculate with this formalism. So we could do that too.
That's an interesting question. If you're probing, for instance, if you're probing sigma x, so that the eigenstates of your probe actually have an uncertainty in rho CC, what would happen?
Yeah, that's a different story. And that's a little bit what I was getting back to before, because you could also imagine measuring, I could also have some coupling to this dot and to that dot. And here's something interesting. Suppose I had equal coupling to all three dots, then it turns out that it's the same as making no measurement at all. Because none of the coherences has changed, because all the measurement is telling you is that the electron is somewhere in the quantum triple quantum dot system, or it's not anywhere in the triple quantum dot system. But if you do that, it turns out that has no effect on any of this. It's quite remarkable. Yeah, but you're in but it's a small tunneling. So the rate, so these rates are fast compared to these guys. Or maybe it's the other way around. So sorry, these guys are slow compared to these guys. Yeah, exactly. Hey, okay. How am I doing? Okay, I have to speed up a little bit. Okay, so so there's also quantum jumps. So the way you do quantum jumps is you turn this QPC into a tunnel detector. So again, measuring tunneling with tunneling. And so the idea is that you have a very steep potential barrier you have to cross to get under this. And then the transmission but then the electron brings your tunnel barrier down. That's an exponential process. So T1 becomes much, much smaller than T0. So when you get an electron click, you know for sure it's empty and not full. Okay, so that's like your photon click detector. And so when that happens, you have a different kind of formalism approach. It turns out you have a so-called jump dynamics, and you also have no jump dynamics. So the jump dynamics is something like this. No jump dynamics is continuous and deterministic. And so that takes this kind of density matrix of all the different possibilities and zeroes out, for example, this central cross, because you know for sure there's no electron there. All right, so that's the jump process, and the no jump process is like this. So then when you solve them, you get this kind of dynamics. So these are like the no jump dynamics here. And then there's like, the blue is like the detector. So here I detect electron, 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 and so on. And then so the little discontinuities of these oscillations when I detect them. So this is actually for the gamma is very small when I have very weak measurements. When I have much stronger measurements, I have this kind of process where I have this kind of jumps. And there are times where I basically, the electron is empty and where it's full, and you jump back and forth between them. So you basically get trapping of electron in the central dot. So that's the kind of solutions you get there. Okay, so I think we started at 10 after, right? So
take another 5 minutes here.
okay, good. So I want to tell you a little bit about the second part of the story. So that's the first part of the story, sort of the foundational aspects of what happens to the tunneling particle while it's being measured. And now we wanted to sort of put a twist on that, because I want to answer that paradox I kind of raised for you in the beginning. If I find it's there, where does the energy come from to make it allowed, right? Because it's energetically forbidden. So if it's there, where does it come from? And basically the idea is it has to come from the measurement. But if it comes from the measurement, you can view the measurement as a kind of energy source that's injecting energy to the system. So if it's an energy source, why not turn it into an engine? So that's the idea behind the second part of the story. And what we're going to do is we're going to take exactly the same quantum tunneling setup we had before, but we're going to change it a little bit. And we're going to add a third lead. And so the idea is that if an electron is on this dot, I can allow transport, now a particle coupling onto this third lead like so, okay? And so this allows us as a way of collecting localized particles of high energy as a harvester of this energy, okay? And what we're going to do is we're going to move to the so-called strongly hybridized regime. So before we were in the co-tunneling regime, when these guys were relatively weakly coupled, now we want to move to maximize this effect to the strongly hybridized regime. This guy acts like a molecule. These guys are really tightly coupled together. So I have excitations of the entire system that are the ones that matter. So it's like a triple quantum dot molecule now for this part of the story. And so again, we can write down the Hamiltonian of just this term. And to make sense of this, we have to diagonalize this Hamiltonian directly. What we find is we find three important eigenstates when it's occupied. The first two eigenstates are superpositions of the left, the right, and the center quantum dot occupation. But there's another one that's really interesting. This state I write as D as an antisymmetric superposition of left and right. So this is also an eigenstate of this Hamiltonian, and for us, this will serve like a dark state in quantum optics. You'll see that in a little bit, okay? So it doesn't, because there's no C here, it's only left and right. All right, and so these parameters here are functions of the Hamiltonian parameters, epsilon and omega. So we can work through this. We can think about calculating Fermi-Golden rule transitions into these states, D plus and minus, using Fermi-Golden rule calculations. There are some rates of hopping into this system. In the interest of time, I'm not going to go through this, but I'll just give you the rates. So we can solve the system of equations. And I just want to give you the results. So the first result is we can think about rectifying the current here. So we can add this other reservoir. And so the idea is that we can think about plotting the current passing through the system IC as a function of the detuning of the central dot, and also this is the detuning of the central dot versus epsilon compared to the chemical potential. And what we see here is that this is for finite measurement strength. We see that there is some current passing through the system that is plotted in this way. Another way of writing that is I'm plotting the current versus this central this is the chemical potential of that central lead as a function of different measurement strengths. So when I have no measurement strength, I get this black line here. So you see the zero bias, there's no current as you would expect. But what's interesting is you turn on the measurement, you start turning on the strength, and you get rectified current. So you start having current that's flowing through the system just being generated by this quantum measurement. Okay, so that's an interesting prediction there. So the fact that you can have rectification here suggests we can make a heat engine. And so, yeah, so we can actually generate power. So we can put a bias across this, this triple quantum dot system to light up a battery, for example, and plot the power that you generate versus the chemical potential of the central dot. And what you find is that indeed you generate power. So we can calculate all the engine characteristics. So this is the power. This is the efficiency of the engine. So if I divide the amount of power I'm generating divided by the amount of energy I inject into the system, we can also have regions where you have positive efficiency. So you're generating power from this engine. So it's converting this energetic source into a heat engine or kind of measurement engine. But we can also refrigerate as well. Okay, so we can also think about if I cool the reservoir. So if I want to cool, for example, the left reservoir, I have 3 of them now. So I cool the left or the right. This is possible using different effects. And I think I'm not going to go through this, but just to say that refrigeration is possible. And there are different dynamical paths that you select depending on where you put these levels compared to the chemical potentials. Something we call checkpoint cooling. We can talk more about that in the questions if you want. And then there's also an absorption refrigerator-like action where you can basically cool by heating, right? This is a classic absorption refrigerator. And by tuning these chemical potentials, we can actually make this to tuning negative to make the tunneling, anti-tunneling effect, and then look at absorption refrigerator effects as well. And then the last thing, what's cool is I think I'll mention, yes, it's checkpoint cooling. I think I'll mention this interesting purification effect. What's interesting is I told you that there's this dark state, L minus R, but if I'm measuring, if I'm kicking around the middle dot, this state doesn't see what's happening there. So if I kick it around, if I couple it to some current, this state doesn't see it. And so if I do some, align my levels just right and measure it a lot, what happens is this state becomes purified. So everything else gets kind of scrambled and removed from the system. And so if I can plot the purity of this state, zeta, for different parameters, and I can find regions where it becomes pure by this sort of dissipative process of taking out all the other stuff except this left minus right dark state. Okay, so I think I'll stop there. So here are my conclusions. So I told you about quantum measurement and quantum tunneling together and how we can learn new things about tunneling and measurement in this combined scenario. Revealing some new predictions that we hope we can see in the laboratory sometime soon. I've been talking to some experimental groups about that. And then this possibility of using the energy the measurement provides in this process to make a heat engine or refrigerator. So thanks so much for your attention.